Unit 1, Part B, Basics of Data Networks. We've gone through the basics of computers. Now we're going to go through the OSI model and look at how computers converse with each other and how data is sent over networks. We'll later figure out how this basic mechanism of sending data over networks has security implications and what we can do about them. The scope of a computer network. You've got local area networks, metropolitan area networks, and wide area networks, and common carrier and ISP networks. The distinctions between these, or at least between the first three of these, are somewhat arbitrary. Local area networks can be defined as a network that covers one single facility. In a geographic sense, it's a network that includes a single local subnet where addresses are locally significant. It's a network where the connections do not require a common carrier to connect to off-site locations, though that restriction has been greatly loosened in recent years. Metropolitan area networks can be defined as a network covering an entire metropolitan area, where it's feasible, say, for a network admin to drive from one end of the network to the other. Wide area networks are networks that involve the services of a common carrier or an ISP, where it's not feasible for a single organization to own the conduit, to own the communications network, etc. And if you are the party providing networking services, you are a common carrier or an ISP. There's a subtle difference between these two. A common carrier is, I believe, a legal term referring to folks like the old phone company and the old telegraph company that were regulated and required under law to provide services, according to a published schedule of rates to whoever agreed to the conditions of those rates. They were meant to be non-discriminatory and were heavily regulated. ISPs are not quite so heavily regulated, but provide a similar sort of service, and if they permit other parties to communicate with each other, they're not strictly speaking a common carrier, though. The components of a computer network involve a computer or some other input-output device, something that generates data that needs to be transmitted. You have something that connects the device to their local network. For wired Ethernet, that's referred to as an adapter and a transceiver. For other networks, there's an equivalent for that as well. Transmission media, how do you get from the computer to the other computers in a network and to the other networking devices? That can be via radio wave, via copper cable, via fiber cable, via optical. And then you have these devices that shuffle the networking traffic between the endpoints. Hubs, you don't see too many of those these days. Switches, bridges, routers, and gateways. They're devices to route and manage traffic between two endpoints. Here's an example of a computer network. You see you have a local area network where you've got three devices connected to a switch here. Those three devices are all part of the same network. They're talking via what we'll soon discuss as a layer 2 protocol. They know each other directly and communicate directly with each other. Now, in order to communicate outside of their own local subnet, they need to go through what's called a router. A router is a device that has the intelligence to know where subnets are located, and if you ask or send traffic to a certain destination, they can point that traffic out to the particular destination. In this case, the router is basically linking that local area network to the wide area network via a CSU-DSU, which is a type of device used with certain sorts of direct circuits that connect you to wide area networks. So in this case, there's only one route, and that is a route out of the network, and everything else stays within a network. The OSI 7-layer model was developed during the 1970s. It was an early attempt to standardize how networking devices communicate. Prior to OSI and similar models, each vendor of computer equipment had their own way for their equipment to talk to their own products. Equipment from different vendors generally wasn't interoperable. You couldn't have, say, an IBM computer easily talk to a digital equipment computer, for example. They all had their own networking protocols and their own networking hardware and software. OSI was an attempt to split up the networking system into specific layers. Each layer above relies on the services provided by the layer below, and is blind to exactly the mechanisms that the layer below uses to manage traffic. So that way all you need, for example, at the application layer is some calls to a process at a presentation layer, and that presentation layer will magically determine how the data needs to be formatted. The application layer doesn't need to be concerned about this at all. So what it does is it isolates layers vertically, and in theory would allow you to replace one vendor's layer with another vendor's layer, and would allow one vendor's layer to communicate with another vendor's layer as well. So it's an attempt to modularize as well as standardize networking and make it vendor independent. How the layers work. They work by, on the sender side, you take some data you want to send and you gradually wrap it or insert it into envelopes that represent each layer: application, presentation, session, transport, network, data link, and physical. And then on the receiver side, you unwrap the various layers, and at the end you end up with some data that gets sent to the corresponding application at the other end. Sort of like this. Application layer traffic gets converted into presentation layer traffic as in a presentation layer wrapper. That gets sent to the session layer. It gets placed inside of a segment for the session layer, managed by the transport layer. The network layer, the segment gets wrapped in a packet. The network layer then wraps in a frame for the data link for the neighbor-to-neighbor communication. And that in turn becomes modulated into a physical layer signal, something that can actually be transmitted over wires, fiber, optics, or radio spectrum. It gets transmitted. The other side receives what's basically a bunch of signals, something having a certain frequency, amplitude, phase, and so forth, takes that low-level electronic information and converts it into data. It then wraps it into a frame at the data link layer, routes it, unwraps the data link layer, unwraps the network layer, unwraps the transport layer, and so on until you end up with the final application level message that was sent initially. Physical layer protocols. They are the signal characteristics. It's the electrical engineering part of communication. You can, in fact, tell the distinction between what's at the physical and data link versus the network layer by which entity develops the standards for it. If it's data link and physical, it's the IEEE, the Institute of Electrical and Electronic Engineers. If it's a network layer and above, it's generally the IETF, the Internet Engineering Task Force. So signal characteristics are frequency, phase, and amplitude. The transmission media is defined at the physical layer: copper, fiber, or radio. And the encoding, which is basically how a 1 or 0, a bit, becomes a change in a frequency, phase, or amplitude. How you map the information to the characteristics of the signal. Now, at the data link layer, it's link-to-link communication, neighbor to neighbor. Of course, neighbors can talk in common. You can have what is, in a sense, a party line, which happens all the time with wireless communication. The basic unit is called a frame. You take the packet that's sent to you via the networking layer, and you add to it frame information, which is the point-to-point address of the destination. The data link layer, because it is point-to-point, involves flow control, ensuring that the sender and receiver are in sync in terms of how fast one is sending and how fast the other can receive. Flow control may involve the receiver telling the sender to slow down or speed up, and them negotiating a rate at which information gets sent back and forth. Error control in some protocols, the receiver double checks. They have error correction codes in what's being sent, and so the receiver can tell if there's an error or not. And there may be a protocol where the receiver will ask the sender to resend the information if there is an error. So, that sort of thing happens at layer 2. Synchronous versus asynchronous. Synchronous is done according to a clocking signal that is synchronized across both endpoints, whereas asynchronous is the sender just sends the stuff, it piles up, and the recipient gets to it in the order it's received, without any sort of clocking signal or anything. And there's rather loose timing with asynchronous. For LANs, it's split into two sublayers. There's a media access control layer, which determines when a device gets to transmit or not transmit. It's kind of a politeness protocol of when it's okay to speak or not speak. And then there's the logical link control, which is how one side actually establishes a link to the other side. Examples of layer 2 protocols are Bluetooth, used in the wireless spectrum for short-range communication between devices. Wired Ethernet, the most common wired LAN protocol currently in use. And in wireless 802.11, the various sorts of Wi-Fi protocols that Wi-Fi routers and switches and so forth use. OSI layer 3, the networking layer. This has the logic that tells the source information how to get to its ultimate destination. It's a roadmap. It says, where do you turn left, where do you turn right, how long does it take to get there, and when have you reached your destination, what's the best route. Think of it as like a Google Maps for network traffic. It understands the roadmap of the network, just like I said. The networking protocol knows what goes where. The basic unit at this layer is called the packet. To a frame is added packet information. Routing information, when you're passing it down, is added to the session information. It includes protocols for updating routes. Things like RIP, OSPF, BGP, etc. tell the routers or routing device what the current state of the network is, what the current configuration is, what's the best way to get from here to somewhere else. Typically, layers 4 and 5 in most current protocols are combined together in a single transport and session layer. They're how the client and server establish a state across the network. It's an open connection between the two endpoints. To the endpoints, this looks like a direct link. In a lot of ways, the session layer mirrors what goes on at the data link, but the data link is actual physical neighbors. This is a link between logical neighbors across an entire network. Most practical protocols combine these into one. It adds session information to the basic application information on the sender side. And it includes application programming interfaces or APIs for use, things like sockets and WinSockets. Now the presentation and application layers. This is where the real work of the application gets done. Again, in most modern applications, these two are combined. You don't have a separate set of presentation layer protocols, with maybe a few exceptions. The application basically determines the presentation in itself. The data portion, it's the data portion of the packet or frame. This is the stuff that actually matters to the endpoint. This is the point of the communication, a reason why the sender and receiver are talking. It's because of these layers. Examples of application and presentation protocols are things like Microsoft Remote Desktop for remote viewing of someone else's desktop and logging into systems remotely with a full graphical interface, FTP, which is commonly used for transferring files, and HTTP, which is the protocol on which the internet is based for transporting web pages. Client-server logic resides at these layers.